So what happens here is A initially comes in contact with the spring, compresses the spring, in the process transfers some momentum to B, and eventually the spring relaxes back to natural length, and because A is not getting fixed to the spring, so eventually A loses contact with the spring again. So the third part is you have to find the speeds or the velocities of A and B when that happens. That is, the spring relaxes back to natural length and A loses contact with the spring again. So just start working on this. We will understand the basics first. So look at A plus B plus the spring as a system, and you can see that we can conserve a couple of things for that system, right? We can conserve the horizontal momentum, actually the entire momentum, because net external force is 0. So that momentum is only one dimensional here. So it's a 1D momentum conservation equation. And we can conserve the mechanical energy, including the elastic potential energy in the spring. So at any in-between instant while they are in contact, if at such a time, let's say A's velocity is VA, B's velocity is VB, and the spring is at a state of a compression of X from the natural length, then the conservation equations are that MVA plus 2MVB should be equal to MV naught. This is our conservation of linear momentum. For our system, which we can take here as the combination of blocks plus the spring. And then, of course, kinetic energy of this one plus kinetic energy of this one plus the elastic potential energy of the spring is equal to the initial kinetic energy of this block. So this is conservation of mechanical energy for the system. Okay, so these are two universal equations we can use at any instant of time. Now we have to adapt these equations to the specific conditions of part 1, 2, and 3. Okay, so for part 1, just substitute VA as plus V naught by 2. Okay, it can, now we'll also discuss later why it cannot be minus V naught by 2. Okay, because in this case A will recoil finally, but its recoil velocity will be less than V naught by 2 in magnitude. So it cannot be minus V naught by 2 when speed is V naught by 2. It has to be plus V naught by 2. So the first equation becomes V naught by 2 plus 2 times VB is equal to V naught. So the speed of this one becomes, as you can see, V naught by 4. And now substitute in the second equation. So VA square, which is V naught by 2 whole square. Second equation we can write like this, that VA square plus 2VB square plus K by mx square is equal to V naught square. So VA we will substitute as V naught by 2 plus VB, which is 2VB, which is 2V naught by 4 whole square plus K by m x square, where x is the quantity we're looking for, is equal to V naught square. So this equation will tell us that K by m x square is equal to, if you take V naught square common, you have 1 minus 1 by 4 minus from here 1 by 8. So that will become 1 minus 3 by 8 or 5 by 8. So x will become V naught into square root of 5 by 8 m by k. So this is the value of x and this is the value of VB at the instant when VA is this much. Now you can try adapting in this, taking the value of VA as minus V naught by 2, but you will see you will get a negative value of x square, which is not possible. That will tell you that it's not possible that E will have a final velocity of minus V naught by 2 in the system. Okay. Moreover, when we come to the third part, we'll understand why that's not possible. Now, how will we solve the second part? What is the condition we will apply for the spring's compression to be maximum? Something very important in this type of question. When the spring reaches maximum compression, is there any special condition about A and B, about their motion?
Velocity will be same.
Yes, very good. Their velocity should be same, or their relative velocity should be 0. So in equation 1 and 2, you put the condition that VA is equal to VB. So the corresponding value of x you will get will be the maximum velocity, maximum compression. Okay, so that's the important thing to pick up over here. You can understand that in this diagram, initially, when VA is greater than VB, A approaches B. Okay, A is approaching B. So the spring is compressing, X is increasing. So X is increasing. Okay. Eventually, VB becomes greater than VA. So B separates from A. So that is when the spring is again relaxing. So X is decreasing. But in between, there's an instant when VA is equal to VB. So at that instant, X is maximum. That is the instant when X is maximum. So that is what we will incorporate in the second part. So when X is equal to X maximum, VA is equal to VB, or relative velocity of A with respect to B is equal to 0 at that instant when the spring is having maximum compression, or A is closest to B. So incorporate that. So from equation 1, you have VA is equal to VB, implying that VA plus 2 times VA is equal to V naught. So VA equal to VB is V naught by 3. Now substitute that in equation 2. So we'll use this form of equation 2. So VA square, which is V naught by 3 whole square, plus 2 VB square, which is also V naught by 3, plus K by M into X's maximum value squared is equal to V naught square. So this will give us the simple relation. This time we have 1 minus 1 by 9 minus 2 by 9. So that will become 1 minus 3 by 9 or 1 by 3 or 2 by 3. So X maximum will become V naught into square root of 2 by 3 M by K in this particular case. This will be at the instant when VA is equal to VB is equal to this. At this instant, this will occur. Okay, now for the third part, how will we find the final velocities when the spring disengages again? So when A finally loses contact with the spring, we have X will become 0. Okay. So we will have half mVA square plus half 2m VB square should be equal to the initial kinetic energy. That's half mv naught square, and momentum conservation, that is mva plus 2mvb is equal to mv naught. But the thing is, we can use a trick here, that this is like the situation where there is momentum conservation with kinetic energy conservation plus kinetic energy conservation. So it is like the situation of a perfectly elastic collision. It's a perfectly elastic 1D collision. So you can also see that means that separation velocity should be equal to approach velocity. So we can use that. So we can use the fact that Vb minus Va should be equal to V naught. And from the second equation, we have Va plus 2Vb is equal to V naught. Okay. So if we just add these two equations, we can see that we'll get Vb is equal to 2 by 3 V naught, and Va will be minus V naught by 3. Now the fact that the final speed of A is minus V naught by 3, that tells you again back to part 1 that it can never be minus V naught by 2, because it's minus 0.33 times V naught. So it cannot reach a value of minus 0.5 V naught. Okay. So no matter what happens, the block A will never have a velocity in the backward direction of V naught by 2, because its final velocity is V naught by 3 in the backward direction. So it can only have a speed of V naught by 2 when it was still on its way forward. So this is back to natural length now, and this is 2 by 3 V naught. So when we discuss more about collisions today, this will be very obvious final result for you. Okay. So here, instead of solving these two equations involving a quadratic equation and all that, we can just use that trick that we know that when kinetic energy is conserved along with linear momentum conserved in 1D, it gives us the property that coefficient of restitution is 1. So velocity of separation will be equal to velocity of approach. This is the condition for coefficient of restitution to be equal to unity. Okay, people. So hope this question is clear in particular. Okay. Now from this, we will move on to collision problems, and then finally we'll come back to variable mass systems to complete. So let's look at collisions next. So we'll start with one-dimensional collisions. So I'll just quickly take you through the equations that you should know, or the direct formula. So we'll just talk about the general formulae. So if a particle m1 with a speed u1 or velocity u1 in this direction going towards a particle m2 like this, such that u1 is greater than u2. So they have an approach velocity of u1 minus u2. And remember, u1 and u2 are with this sign convention. So for example, if m2 is traveling in the opposite direction, then u2 is substituted with a negative sign in this. Okay. Then after impact, so after they come in collision, so some kind of collision impulse acts like this, eventually their velocity, suppose, now we are assuming they're in the same direction, but v1 might become a negative quantity also, in which case it will come with a negative sign. So it will be in the opposite direction. So now what will happen is after impact, the separation velocity becomes v2 minus v1. So for perfectly elastic collision, you know that kinetic energy is conserved, and that implies that E is equal to 1, or separation velocity is equal to approach velocity. So when we incorporate that, we get the relation that m1 u1 plus m2 u2 is equal to m1 v1 plus m2 v2. And in general, E is equal to v2 minus v1 upon u1 minus u2, that is equal to 1. So when we incorporate these two, we get the direct result for perfectly elastic collision, that v1 is equal to, you should know this formula, m1 minus m2 upon m1 plus m2 plus 2m2 upon m1 plus m2 u2, and v2 is equal to 2m1 upon m1 plus m2 plus m2 minus m1. Okay. So find some kind of trick to memorize this formula if possible, because it will save you time of solving equations, especially at the JEE Mains level. So these formulae are coming by solving this equation 1 and 2. By solving this, we get this. And a very important special case of this formula is that if m1 is equal to m2 and coefficient of restitution is 1, perfectly elastic collision, then v1 becomes u2 and v2 becomes u1. So whenever we have equal masses making perfectly elastic collision, there is exchange of velocities, momenta, kinetic energy, etc. Everything is exchanged between the two particles. Another special case you should remember of this is that if u2 is 0, so a particle m1 moving with velocity v0, let's say, is coming and hitting another stationary body at rest, and E is equal to 1. So in this case, v1 becomes m1 minus m2 upon m1 plus m2, and v2 becomes 2m1 upon m1 plus m2. So in this, you can see that v1 will be negative if m1 is less than m2. So if a body like this, collides with a heavier body at rest, and the collision is perfectly elastic, of course, E is equal to 1 in this particular case. Okay. Then it recoils. So if m1 is less than m2, there is a case of recoil, whereas v1 is positive if m1 is heavier than m2. So it continues in the same direction. It does not recoil. It only slows down. So there's another interpretation of this equation that you should keep in mind, apart from the direct formula. Okay, now next let's come to the inelastic collision. Not perfectly inelastic, but inelastic. So inelastic collision is one where there is loss of kinetic energy. Okay, or in general you can say there is dissipation, and the coefficient of restitution becomes less than 1, but at the same time greater than 0. So if E is known, then we can always use this formula that M1U1 plus M2U2 is equal to M1V1 plus M2V2, and E is equal to V2 minus V1 upon U1 minus U2. So in a situation where the value of E is known to us, we can use these, solve, and that gives us the direct formulae, which are slightly adapted versions of the above formulae. So instead of M1 minus M2, this term becomes M1 minus EM2 divided by M1 plus M2. Okay. And this becomes, instead of 2M2, it becomes 1 plus EM2 upon M1 plus M2. And similarly, this term becomes 1 plus EM1 upon M1 plus M2. This term becomes M2 minus E times M1. So in fact, these formulae that we have written, you can think of this like the universal formulae, because this will give us the same thing if we substitute E as 1, okay, for the above formula also. So this formula here, this set, this is just the special case of E equal to 1 when you substitute the lower formula. Okay. So you can think of this like the main set of formulae. And finally, if you have the perfectly inelastic collision, that means the two bodies stick to each other, or the two particles colliding stick to each other. So this is the situation in which there is maximum loss of kinetic energy. In which particular situation the dissipation of kinetic energy will have maximum value? When they stick to each other. So when they stick together, you can see that their final velocities will become a common velocity. So that common velocity will just become the system's initial momentum divided by the total mass. Just the momentum conservation equation will tell you this, okay? Which you can see you'll also get by substituting E equal to 0. This, if you substitute E equal to 0, it will give you this formula that V1 is equal to V2 is this whole term, M1 U1 plus M2 U2, whole thing divided by M1 plus M2. So especially at JEE mains level, it is important to remember these formulae, or at least know how to use these equations to develop the formulae fast, because you will get direct type of questions. So let's look at an example problem. Okay. So given M1 is equal to 5 kilograms, B0 is equal to 12 centimeters per second. Now if M1 makes a perfectly elastic collision, head-on impact. Head-on is the same thing as one dimension. find m2 if m1's final speed is 6 centimeters per second. If m1's final speed or final velocity has a magnitude of 6 centimeters per second, then how much is m2? Okay, the surface is smooth, so there's no friction involved. Yeah, so in this answer, Sparsh and Nishit, both your answers are correct. But one thing, there are two possible answers. Okay, because it's saying that the final speed is 6 centimeters per second. So it could be in either direction.
Oh yes,
So if it makes a collision with a lighter body, then it will continue in the same direction at v naught by 2. But a heavier body, it can also recoil. So you have to consider both the cases. Consider both the cases where,
5/3 and 15.
yeah, one case is this, yeah, after impact, something like this, and one case is assuming that this is a heavier body, so it continues in the same direction. So if you take this case, you can just use the fact that E is equal to 1. That means V2 minus V naught by 2 has to be equal to V naught. Separation velocity is equal to approach velocity. So V2 has to be 3 by 2 V naught. Okay. And then use momentum conservation. So M1 into V naught by 2 plus M2 into 3 by 2 V naught has to be equal to M1 V naught. So 5 by 2 plus 3m2 by 2 has to be equal to 5. M2 is 5 by 3 kg. So this is the first solution. Whereas here, E is equal to 1 means separation velocity V2 plus V naught by 2 is equal to approach velocity V naught. In this case, V2 will be V naught by 2. So your M1 V naught, the initial momentum, will be equal to minus M1 V naught by 2 plus M2 into V naught by 2. So M1 1 plus half V naught is equal to M2 V naught by 2. So here the relation will become 3 by 2 M1 is equal to M2 by 2. So M2 will be as much as 3 times M1 or 15 kg. And this is what you were getting?
Yes, sir.
Yeah, okay. So two possible answers. That's the only thing we have to be careful about in this question. And also, like, you can always use this trick that separation velocity is equal to approach velocity. Instead of doing the kinetic energy conservation, you can. Right. Now you can also get a question where coefficient of restitution is not given, and instead we have to use some kind of energy relation. So you could have a situation like this, where a body of mass m going with a speed v naught collides with, let's say, another identical mass at rest, and it is a head-on inelastic impact such that 25% of kinetic energy is dissipated due to the impact. So from this we have to find final velocities, and we have to find the coefficient of restitution. Okay, so supposing after impact, the velocities v1 and v2, so we use the fact that momentum is conserved, so and 25% kinetic energy is dissipated. That means the loss in kinetic energy is 0.25 of half mv naught square. Yeah, so we need the coefficient of restitution. No? V1 will be 3 by 4 into V, is it? So what about the coefficient of restitution? Just try that out first. So the loss of kinetic energy is 25% of the initial kinetic energy. That means that the final kinetic energy is 75% of the initial kinetic energy, or 0.75 of half mv naught square. Okay, so half mv1 square plus half mv2 square, the final kinetic energy is going to be 0.75 times the initial kinetic energy. So you can write this like this, that v1 square plus V2 square will become 3 by 4 V0 square. So now what we can do is we can solve these. So when you solve, you will get a set of equations. So you can take V1 as suppose X. So V2 becomes V0 minus X from equation 1. So you have X square plus V0 minus X whole square is 3 by 4 V0 square. So get this quadratic equation 2x square minus 2 V0 X plus you'll have V0 square minus 3 by 4. So 1 by 4 is 0. So from this you can see that your X will become like this. Now you can see the two roots. One of them will be V2 and that will be the larger one. So that will be, and the other one will be V1, that will be the smaller one because they have to separate after impact. Okay. So V2 has to be positive, V1 is the negative one here. Basically V2 has to be greater than V1. Okay. So first, these are the values of V1 and V2. Just check your solution. Okay. And now from this, we can calculate the coefficient of restitution. So we can see that separation velocity, which is V2 minus V1, will become root 3 times oh sorry, I made a mistake here. This is by 4. This is by 4. So there's a factor of by 2 here. Yeah. So this minus this will give you an approach velocity was V0. So coefficient of restitution is root 3 by 2. Okay, now there is another approach we can take to solving this question. The other approach we can take is let the coefficient of restitution is some E, which we have to find out. Okay. So then my V1 and V2 we can write in terms of the coefficient of restitution. V1 will become 1 minus E by 2 times V0 and V2 will become 1 plus E by 2 times V0. How I know this? I know this from the formula. In that I will put U1 as V0, U2 as 0, M1 equal to M2 equal to M. and E is equal to E. So you'll substitute this and you'll get this. So now you can see that the final kinetic energy is equal to 0.75 times the initial kinetic energy. So half mv1 square this. Okay, so we have v1 square plus v2 square is equal to 3 by 4 times v naught squared. And that we substitute these values in terms of E. So that will give us E first of all, and then we substitute that E back here. So that's another approach we can take. So this is an easy approach. Okay, so this will just give us we're getting a different value now. Okay, I'll just check the solution there. So this appears to be giving us the value of E as 1 by root 2. So if E is 1 by root 2, we're getting a different E over here. Okay, I'll just have to check the numerical calculation. Somewhere, either of the two, there is a mistake. Yeah, so there does appear to be a mistake.
Sir, in that under root, like
Uh,
solution for x, it should be 4v naught square minus 2v naught square, no?
right,
4,
right, right. That is
4
the
AC.
mistake. Yeah. So these are the values now, V1 and V2. So this should have been this should have been 2. That was the mistake. Right. So anyway, This will give us the same thing as this. One minus 1 by root 2. This. So from this also we can see that separation velocity is v2 minus v1. So that will become v0 by root 2. So E is equal to v2 minus v1 upon v0. So 1 by root 2. That matches this. Okay. So this was the other approach, that you assume some value of E and solve in terms of E. And then you apply the condition that there is 25% loss of kinetic energy. And solve for E first, and once you got the value of E, you know V1 and V2. V1 is 1 minus E by 2 times V0. So it become V0 by 2, 1 minus 1 by root 2. And V2 is 1 plus E by 2. Which is the same that you are getting by solving this. So this type of situation is when coefficient of restitution is given to us. Loss of kinetic energy is given to us, and we have to calculate coefficient of restitution. Okay. So this is your head-on collisions. Now let's move on to collision of particle with a plane, rigid surface or plane. That is also very important at JEE level. In fact, that in combination with projectile concept. So the second type of collision of a particle with a rigid surface. Okay. So here we are not talking about collision of rigid bodies. That will come in the rotational mechanics chapter later, because then we have to talk about angular impulse also. But here we are treating everything like a particle, so it's only linear impulse, linear momentum. So anyway, normal impact, or when the impact is perpendicular to the plane of the surface. So we have a rigid surface like this, and a particle moving at a speed v0, such that its velocity is perpendicular. So when this happens, then at the impact point, the collision impulse will act along this line only. So it will transfer momentum in the same direction. So the particle will, after impact, end up moving with some velocity v like this after impact. So the separation velocity will just become E times the approach velocity. So when there is E equal to 1, then there is conservation of kinetic energy. Once again, because V becomes V0. Whereas E is equal to 0, there is 100% loss of kinetic energy. Maximum possible loss of kinetic energy. In this case is 100%. Whereas when we have the oblique impact, so in that situation, if this is colliding such that with respect to the normal at the point of impact, this angle is theta, like an angle of incidence, then what happens is as the collision occurs, the impulse transferred is in this direction. It's along the normal. Okay. So the tangential component of momentum will remain conserved. So this impact momentum that it had. So V naught cos theta, this is the normal component of velocity, and this is the, in fact, the approach velocity. Whereas V naught sine theta, this is the tangential component of velocity. So after impact, what will happen here is that the tangential component will remain conserved, and the normal component will depend on the value of coefficient of restitution. This angle was theta. In general, after impact, if it goes off at an angle phi like this, with a velocity v, then v cos phi, it is the separation velocity. So v cos phi will be E times v naught cos theta. And v sin phi, it is the tangential component. So this remains conserved because the impulse is only along the normal direction. So v sin phi will be equal to v naught sin theta. So if we take our x and y axis like this, such that x axis is the normal axis and y axis is the tangential axis, then we can see that the initial velocity is v naught cos theta I cap plus v naught sin theta j cap, whereas after impact, the final velocity becomes minus e v naught cos theta plus v naught sin theta j cap. And this term only is our v sin phi, and this term is our v cos phi. So from this we can also see that E is equal to 1 means that V becomes V naught and phi becomes equal to theta. Whereas E equal to 0, for example, means that V is equal to V naught sin theta and phi becomes pi by 2. Okay, so basically in this case, the particle sticks to this and moves parallelly with a final velocity of V naught sin theta. Whereas here it is like a mirror image reflection, like a reflection sort of case. It's a reflection with 100% conservation of kinetic energy. And any general case where E is less than 1 but greater than 0, there will be some loss of kinetic energy, and phi will be greater than theta but less than 90 degrees. So these are the special cases of collision with, the oblique collision, which you should remember. Okay, so now the most common type of question related to this is collision of projectile or a particle in projectile motion with a surface. So let's start with the example of horizontal surface. So if a particle is projected like this at a speed of, let us say, 100 meters per second at an angle of projection of 53 degrees, and it bounces like this. So every time it collides, the coefficient of restitution is 1 by root 2. So we have to find the range and maximum height between A and B. That is the first impact and the second impact. And then once again, the range and maximum height between B and C. Okay. Take G equal to 10 meters per second square. Standard value. Okay. Just try this out, people. Okay, I'll just verify the answers. Yes, that's correct, Nishit. Both the answers are correct. Okay, so very good. So, in a problem like this, what you can do is you can use the component method of calculating the different parameters of a projectile. So if the vertical component of projection velocity is ux and the horizontal component is ux, the vertical component is uy, then in general, you can use this formula that time of flight is 2uy by g. Range is ux into time of flight. So it becomes like this. And maximum height becomes uy square by 2g. So now for the impact, you can use this simple concept that as the projectile impacts, the impact velocity is such that your approach velocity is ux and your tangential velocity is, sorry, the approach velocity is, or the normal component of velocity, that is your uy, this is ux, same as the projection velocities uy and ux. So after this, when it goes into projectile again, after the bounce, the projection velocities become such that this becomes e times uy, whereas this, what happened? This remains conserved. Okay. So that is why now, if after the first impact, you take this to be R1 and this to be H1, now you can see that at E, this will be the same as the initial one, which is 60 meters per second. But so this will become 80 by root 2 or 40 root 2 meters per second. Okay. So this R1 will become 60 into 2 times 40 root 2 by G. And your H1 will be and second time around what will happen is, if here this is uy double prime and this is ux double prime, so this mu height and this mu range so this remains conserved, but this component becomes e times uy prime or e times uy, so it will get further multiplied by a factor of root 2. So this becomes the case. Okay. So now your new range will become 60 into 2 times 40 by g. So it will become 480 meters. And your new maximum height will become 40 square by 2 into 10. So it's going to be 80 meters. So in general, you'll see it follows a series like this, that your H1 will be E times H and your R1, sorry, E square times, and your R1 will be E times R. This kind of progression continues. It's like a geometric progression. Give me a second, guys. restart the program.
So what was the relation between H naught and H1 and
I'll
H2?
tell you. Okay. See, it all comes from understanding how it depends on UX and UI. Because with each collision, your UX is remaining conserved, but your UI is getting multiplied by a factor of E, na? Right? So now when you look at the formula for maximum height, na, it depends on UY square. So that is why your maximum height will get multiplied by a factor of E square. Okay. Whereas if you look at your range, it depends on UX into UY. Now UX is remaining conserved, but UY is becoming E times. So it becomes like this. So after the next collision, your H2 will become E squared times H1, or that is E to the power 4 times H. Whereas your range will be E times R1 or E squared times R. So like that, after the nth impact, your height will become E to the power 2n times the original height. And your range will become E to the power n times the original range. Right, this is going to be a GP where your height keeps decreasing by a factor of E square every time, and your range keeps decreasing by a factor of E every time. Why? Because your height depends on U square, UY square, and UY decreases by a factor of E. Whereas your range depends on the product of UX and UI. UX is remaining conserved, but UI is getting multiplied by a factor of E.
Okay, sir.
No, clear? No? So just remember this kind of progression. So it all comes from this thing. Even time of flight, it will become like this. If the original time of flight was 2 uy by g, so your time of flight between first and second collision will become E times t. Then your time of flight between second collision and third collision will become E times t1 or E square times t. So like that, time of flight will also have a common factor of E, whereas height will have a common factor of E square, like this. Okay, so this is this. Then another important type of collision problem is where there's an inclined surface involved. So this is also very common at the JEE level. So let's look at straight away a numerical example of this. So we have an inclined plane of 30 degrees with respect to the horizontal, and we are dropping a particle from a height of 20 meters. We drop it from a height of 20 meters. Now what we observe is that immediately after impact, the particle goes off with a horizontal velocity. So the velocity of after the collision is horizontal. So the particle dropped from 20 meters onto the inclined surface. Okay. Impacts and has horizontal velocity v just after impact. So first find the value of v, then secondly find the coefficient of restitution, and then third we have to also find that as the particle goes like this, find the range from A to B. Take G as 10. So again, this is a very common type of application. So see, the main concept you have to use here is that the collision impact impulse will be in which direction? The impact impulse or the collision impulse
Normal to the surface.
is along the normal. So that means we can conserve momentum's tangential component. Before impact and after impact, we can conserve the tangential component of momentum. So that is the main thing you have to understand, that as this particle collides here, the collision impulse is acting along this direction. So the tangential component of momentum should be conserved. This is the tangential direction, this is the normal direction. So now you see, before impact, the velocity was, just before impact, it was V0, root 2 GH. Yeah, Nishit, the coefficient of restitution will not be tan 30 beta. It will come out to be tan square 30 when you calculate. Yeah, so this was root of, so this is 20 meters per second because we dropped it from a height of 20 meters. So this was the impact velocity. Okay. Now the impact velocity is such that with respect to the tangential direction, it has an angle of 60 degrees. This is 30. Okay. So the tangential component of velocity is how much? It is V0 cos 60. So that is 10 meters per second. Okay. Now immediately after impact, we are seeing that the velocity is horizontal. This is the velocity. And that makes an angle of 30 degrees with the tangential direction. So the tangential component of velocity here should be V cos 30 or root 3 by 2V. Now this should be conserved. Okay. So V cos 30 should be equal to V0 cos 60. In other words, root 3 by 2V should be equal to 10. So that tells us something, that V is 20 by root 3 meters per second. Okay. Now once we know this V, we will calculate also the separation velocity and the approach velocity. Now separately from this, you can see that the approach velocity is V0 cos 30, because this angle is 30. So it is 10 root 3 meters per second. And from this you can see that the separation velocity is along this normal direction. So it is V sin 30 or cos 60, whatever. So it is 20 by root 3 to half. So it is 10 by root 3. So once we got this approach and separation velocity, now we will see that our coefficient of restitution, which is this ratio, will become 1 by 3. In fact, if you calculate everything in terms of theta instead of 30 degrees, you will get E as 1 by tan square theta. Tan square theta. Like this. Because we don't need to memorize this value tan square theta or something, because you can get a different case where the velocity is not exactly horizontal or something, but just need to remember the process. So tangential component is conserved. Tangential component of momentum is conserved. That's one concept we are using, and the coefficient of restitution is the ratio of separation to approach velocity. That is the second concept we're using. Okay, now as far as the range is concerned, I just brought this question up about how we can solve it with minimum effort. Okay, so since the component, I mean the projection velocity, from that point is like a horizontal velocity. So don't get into oblique components and all. Just use the fact that it is a horizontal projection on an inclined plane. Okay, and take your x-axis to be horizontal only. It will be much easier. Why? Because if you take this direction to be your x-axis and this direction to be your y-axis, so this velocity we've just got above, it was I think 10 by root 3 or whatever. So v was 20 by root 3, right? Okay, now as this goes like this and collides somewhere here, wherever it collides at this point B, if this range is r at the point B, according to our coordinate system, this angle being 30, okay, the point B should have coordinates x equal to r cos 30. So that is root 3 by 2r, and y coordinate as r sine 30 is r by 2. And our projectile equation is such that x should be equal to vt. So that is 20 by root 3t, and y should be equal to half gt square. So that is equal to 5t square. So the relationship between x and y should be that y is equal to 5 times root 3x by 20 whole square. So that is 3x square by 20 into, so 400 by 5, so that's 80. This is the relationship between y and x. This is the equation of trajectory according to this coordinate frame, where x is this direction, y is this direction. So now substitute the point B's coordinates. So at B, y which is r by 2 should be equal to 3 by 80 into x square, where x is root 3 by 2 r. So from this we can just easily find out r. So this is the easiest way of calculating the r. Okay, so this is about your oblique collision type of situation between a particle and a rigid surface. Now let's come to the third and final type of collision. Oblique collision between two particles or bodies. Or spheres or disks or these kind of things where there's no angular impulse involved. So the general concept, but in particular, if we have a situation like this where we are considering one of them to be at rest initially, then there is a sort of a general method we can develop. So if this one is traveling with a velocity v naught, and this one is at rest. Now this need not be tangential at this point, it could be anything. Okay. But it's not passing through the center of the second one. So when they come in contact, then the center to center line, that becomes what we call the axis of the collision or line of action of the collision force. So the center to center line, that is the line of action of the collision impulse. or in simple terms, we can just call it the line of impact. Because the collision impulse that acts along this direction. Okay. So if the initial velocity of the first one, that one is at an angle of theta with respect to this, okay, then what we can do is we can divide the initial velocity v naught into these two components. This component becoming v naught sine theta. So this is the tangential component. And this component v naught cos theta. This is the approach velocity. So after impact, what will happen is that this body M1 will have a tangential component which will remain conserved. This will be v naught sine theta. This will be conserved. Okay. Whereas it will have a component along this direction, which is, let's say, the normal component. And this other body will have a velocity v2, which is along this line of impact. It started from rest. Okay. So here what will happen is that our separation velocity will become v2 minus vn. Okay. So then we can use this simple result that v separation should be equal to E times V approach. So that means V2 minus Vn, that is our separation velocity, should be equal to E times V naught cos theta. That becomes our first equation. And also conservation of momentum along line of impact. Along this line on which the impulse is acting, this line of impact, along this direction, if we conserve the momentum, we can see we'll get the equation. Here it was m1 v naught cos theta initially, and here it is becoming m1 v tangential, sorry, v normal plus m2 v2. So if you see the solution of equation 1 and 2, solving equation 1 and 2, it is just like that head-on impact. It's like that situation where this was coming at a velocity, and the coefficient of restitution was E. So in this case, our V1 would come out to be what? M1 minus E M2 upon M1 plus M2 V naught. And our V2 would come out to be 1 plus E M1 upon M1 plus M2 times V naught. Now in this case, along this axis, you have to just replace this V naught with what? V naught cos theta. And you have to replace V1 with what? The normal component of V1. So this normal component of V1 will come out to be M1 minus E M2 upon M1 plus M2 into V naught cos theta. And the second one will just come out to be 1 plus E M1 upon M1 plus M2 V naught cos theta. So now see, we know the tangential component. So for the second one's velocity, for the first one's velocity, it is the combination of the tangential component plus the normal component. So its speed will become, okay, where we know that the tangential component here is V naught sine theta. And from here we know the normal component. And V2 is directly this. So this is the general method of solving. Okay, now, obviously, in certain cases, theta will be directly given to you. In certain cases, we have to calculate it by geometry. So we'll come to that also. But the important thing is that when this oblique collision happens, you can divide the motion at the time of impact into two components, normal and tangential. So along that normal line or along that line of impact, it's basically a head-on collision happening. And along the tangential direction, what is happening is there's conservation. There is no impulse along that direction. So whatever component of momentum was there along the tangential direction, you can conserve it. Whereas whatever was happening along the line of impact, you just treat it like a head-on collision between the two bodies. So you get the answers from the head-on collision formula. Okay, so just go through this once and then we'll discuss a numerical example. Okay, so let's see a JEE Advanced type of typical question involving oblique collision. So A and B are identical spheres, mass m each, and radius r each. Okay, on a smooth horizontal surface. B is at rest and A moves at V naught, making an inelastic oblique collision with what is called impact parameter P equal to 1.2 times R. So impact parameter means basically the perpendicular distance of the line of the velocity V naught, line of action of that velocity V naught with respect to the center of B. It is the perpendicular distance of line of action of that velocity vector v naught with respect to the center of the body B. So that thing is called the impact parameter. So if the impact parameter is 0, it would have been a head-on collision. Okay, but here it is 1.2 R. So we have to calculate, and also given to us the coefficient of restitution, and E is equal to 0.5 or 1/2. So find VA and VB after impact, and also find the angle between the vector VA and VB. That is the divergence angle between the separation velocities. They separate out diagonally like this. So the angle between those velocities, that is what we have to calculate in the second part. So just work this out carefully. You will have to make a diagram and understand the, at the time of impact, what the geometry looks like. And what is the angle that the line of impact is making with respect to V naught. You'll have to work that out from the impact parameter given. Yeah, so Nishit, what is the angle you have got for the line of impact with
37
respect?
degrees.
Yeah, 37 degrees. Very good. That's correct. So you'll see that at the point of contact, we take the center to center line. This is 2R, and the velocity of this one was along this line. which was at an impact parameter of d. So now this angle theta, you can see theta is sine inverse of d by 2r. And d was given to us as 1.2 r. So that is sine inverse of 3 by 5. So that is 37 degrees. Okay. So once we know that, we can now compare the before impact and after impact picture. So before impact, this was the situation, and this was the line of impact. So you can see that the approach velocity is V naught cos 37, so 4 by 5 V naught, and the tangential component of velocity is 3 by 5 V naught. Whereas after impact, what will happen is that this will have a V2, suppose like this, and this will have a normal component like this and a tangential component like this. So we can see that the tangential component remains 3 by 5 V naught conserved. Okay. But the separation velocity becomes V2 minus Vn. And this should be equal to E times the approach velocity. So using this concept and the momentum conservation along the line of impact, we can see that our Vn will come out to be m1 minus em2. So that is 1 minus e by 2 times 4 by 5 v naught, because that is our approach velocity. So this will become 1 minus half, so that's half. So it will become v naught by 5. And our v2 will be 1 plus e by 2, because our m1 is equal to m2 is equal to m, and e is equal to 1 by 2. So this will become 3 by 4. So this will become uh, 3 by 4 of this. So 3 by 5 v naught. So these are the answers. Yeah. So 3 by 5 v naught you got, and now we have to calculate the net velocity of this one. So this particular body,
Tangential plus the V naught by 5 is
its net velocity will become the vector sum of these two. So our v1 is, let's say, in something like this. So the tangential was this, and the normal is this. So we can take v naught by 5 common. We'll have root 10. Or yeah, so we can just leave it this way. Or that's the same thing as root 2 by 5 v naught. So this is the speed of the first one. And second one, though, obviously we've got this one. Now about the angle, we can do it this way, that you can treat this as your x-axis and this as your y-axis. So then we can write our v2 as a vector as 3 by 5 v naught I cap. v1 as a vector will become that tangential component and the normal component. So the normal component is v naught by 5, and the tangential component is 3 v naught by 5, like this. So now the angle between the two velocities we can calculate like this by using the dot product concept. So if the second one is having a velocity in this direction, v2. The angle between these two, this angle, let's say it's phi. So you can just calculate cos phi as v1 dot v2 dot product with divided by v1 v2. So the dot product you can see will give us 3 by 25 v naught square. V naught square will cancel out. To v1's magnitude root 2 by 5 into v2's magnitude 3 by 5. So this is 3 by 25 into 5 root 5 by 3 root 2. Something like this. So this will be the value of cos phi. So phi will come as cos inverse of something here. So I think that will be 1 by root 10.
Yes, on that.
So this is the sort of general way of solving an oblique impact like this. Okay, so this more or less covers collisions of all types. So hope all the concepts were clear to all of you in this example.
Yes, sir.
Yeah, good. Now one final type of collision you can have is something where it's a little bit more specific. It doesn't come in this general categories of collisions. Where something like this is happening, there is a rigid body like a block or something, or more like a wedge, that is colliding with a particle, and the wedge is on a rigid surface. So it is forced to move only along the surface. So something like this happens. So like we have a wedge of mass capital M on a smooth surface, and a particle of mass small m is dropped onto it. So in this type of situation, what will happen is when they come in contact, the collision impulse is in the normal direction. But the ground also applies an impulse. So we cannot conserve overall momentum for the system. So this is the collision impulse. But this impulse has a downward component on the wedge. So that downward component gets absorbed by what the ground is applying. So this is like an external impulse on the system due to the ground. Okay. So the system's momentum overall cannot be conserved. So what we do instead here is that for the system, horizontal momentum is conserved. Whereas for the particle, small m, now for the particle, what is happening on that, the impulse acting is only in the normal direction. So if this is the tangential and this is the normal, for the particle, the tangential component of momentum is conserved. So that will give us a second equation. This will give us a first equation. And then whatever coefficient of restitution upon V approach.
So I will the tangential conserve for the particle.
Because particle पे जो collision impulse लग रहा है ना, that is only normal.
Okay, हाँ तो उसका change
So that is the logic that we use. Okay. So this is because the external impulse on the system at the time of impact is vertical. Okay. Whereas this is because the collision impulse on the particle, that is along the normal. Okay. And this is by definition. So now, for example, what is happening is that when the particle collides with this, so it's about to hit, if it has a velocity v naught like this, and this angle is theta. So we can see that this angle is theta, and after impact, let us say this has a velocity v like this, and the particle develops a velocity such that it has horizontal component vx and vertical component vy. So once again, this angle will be theta, this angle will be theta, because this angle is theta. So horizontal momentum conservation for the system, that first equation, what it will give us? It will give us that small m vx is equal to capital M v, because the system's horizontal momentum is 0. So that's the first equation. Then momentum conservation along the tangential direction for the particle, that will give us what equation? So here you can see the tangential component for the particle initially is mv0 sine theta. Now here it is a combination of vx and vy. So we have to calculate the tangential like this, the net velocity component along this tangential direction. So that is mvx cos 30 or cos theta, but minus vy sine theta. So this is our second equation, which is the tangential component of momentum conserved for the particle. M will obviously cancel out on both sides. Okay. And the third is the separation velocity and the approach velocity. So here you can see the separation velocity. So for that you can do like this. If you're in the frame of the wedge, what does the velocity of the particle look like? This becomes Vx plus V, and this component becomes Vy. And this is the normal direction. So you have to find the net velocities component along the normal direction. So your separation velocity is going to be Vx plus V sine theta plus Vy cos theta. Now that should be equal to E times the approach velocity. So that will become E times. Now in this diagram, you can see the approach velocity is the normal component of this velocity. This is the normal direction. This is the tangential direction. So it is V naught cos theta. So this is your third equation. Okay. And you have the three unknowns, Vx, Vy, and this thing, V. So three equations, assuming that coefficient of restitution is given.
So what do you do in the second equation? Can you go through
In the second equation, see what is happening now. We have to conserve the momentum of the particle along the tangential axis.
Okay.
Okay. So in the first diagram, you can see before impact wale diagram mein, initial wale diagram mein, tangential axis is this. So the component of momentum is how much? mv naught sine theta. Okay. In the second diagram, it's a little complicated. The net velocity of the particle is the sum of vx and vy, no?
Yeah.
So वो net velocity ka we have to now find the tangential component, the component along this tangent. So we have to divide those two vx and vy into their components and then sum up those components.
Okay, sir.
You know, so that vx cos theta is along my positive tangential axis and vy sin theta is along the negative tangent. So the net tangential component becomes the difference of the two. Okay, no?
Yes, sir.
Okay. And similarly, the third equation also, what I'm first doing is I'm getting into the frame of the wedge. So in the frame of the wedge, the relative velocity of the particle has got horizontal component like this and vertical component like this. And now I have to find the component of its relative velocity along the normal axis. And this is your normal axis. So I have to find the vector sum of these two's component along the normal axis. That is going to give me my separation velocity. So is it clear?
Yes, sir.
Okay. Now sometimes a subset of this type of question is where it tells you that after impact the velocity of the particle is horizontal. So your Vy just becomes 0. So these equations become easier to handle. Okay. But the general method is this. So in the general method, you will be given the two masses and you will be given coefficient of restitution. And all these three are unknown. So you need these three equations to generate it. Okay. And of course, theta angle will be known. So this is that specific type of problem. Right. So hope this is fully clear, people. Okay. So with this, we complete collisions. Okay. So we'll conclude here today. next session we pick up, we'll do the variable mass system, which will take about a half an hour or so, and then we'll move on to rotation. So can you people like do the basics of rotation, like the like the formulae for moment of inertia, the basic theorems of moment of inertia and all that, so that
Yes,
we
sir,
can pick
okay.
it up from torque onwards, right?
Yes, sir.
So we'll focus on problems for rotation for the early part before angular momentum, right?
Yeah, okay, sir.
Okay.
मतलब torque का formula, ठीक है, then moment of inertia theorems and all that, you revise these things and come so that we can
Parallel axis,
start with the
perpendicular axis.
yeah, it is, sorry,
No, sir, okay.
okay. ठीक है, so I will try to keep a lecture either on Wednesday or Thursday, one of the 2 days. That will be fine,
Yes, sir.
Yes, sir.
right? Okay, then that's it for today, people. All the best.
Thank you, sir.
Thank you, sir.
Okay.